with one voice because the messages from this talk are very similar to the previous talk. So I'm interested in being able to give a physical explanation of an image. So why does this, admittedly not very natural image, look the way it does? I'm also interested in to what extent the human visual system does this. So do we really estimate and maintain a 3D model of the thing we're looking at? And so today's interesting for me from that point of view. Okay, so we've actually just seen a very similar diagram showing the different ways we might start to decompose an image. So at one level, we might decompose it into its kind of intrinsic reflectivity, the color at each point on the surface, and we could go further with how specularly reflective it is and other parameters like that. And its shading. And a typical assumption would be that the appearance is a product of these two things. And this task in computer vision is called intrinsic image decomposition. So this is useful because this is an intrinsic property of the surface, the reflectivity. So maybe that's a good representation for recognition. But we can go further. So the shading is a function of the geometry represented somehow as a normal map here, and the lighting. And in order to reason about this, we need a reflectance model. So here's Lambert's law, the simplest reflectance model for a diffuse surface, which allows us to talk about how geometry and lighting interact, how light is reflected from a surface to give rise to shading patterns. And I spent my PhD working on this task, so trying to extract a normal map from an image, usually images that look like this, right? If you try to do it directly from this without reasoning about this, then you're running into lots of problems. And this is a famous classical computer vision problem called shape from shading. So I've kind of come to the conclusion that you have to reason about everything together, and this is sometimes called inverse rendering. This is what I'm going to be talking about today. So from a single image, can we estimate geometry, illumination, and albedo, the reflectivity of the surface? But I don't want to do it for lab images like this. I spent my PhD doing that, and even under really, really restrictive conditions, we got nowhere with this problem. We understand it really well mathematically, and we can't solve it to a satisfactory degree. I want to do it for images like this. This is York Minster, where I'm from. So in the wild, really uncontrolled conditions, really challenging scenes. And I want to estimate all the stuff I said before: geometry, material properties, illumination, shadows, and so on. And if you could do that, you can do things like edit the pose of the image, like change the lighting, lots of other useful things. The problem is, as was hinted at in the last talk, we know that the way to solve this problem is with deep learning. And well, okay, there's probably other ways, but we know that deep learning does well on some of these tasks already. So we can get depth maps from LiDAR or something. So if you have a lot of money, you can go out and get millions of images and LiDAR, and you can recover a depth map. You're going to hear a talk next on monodepth, so that works. I would even argue, for faces, you can get the data. If you've got lots of money, you build a light stage, you collect loads of data, and you can train a deep network to do this. But if I want to do it for this scene, where do I get the albedo map? How do I get a good estimate of the lighting outdoors? And then can I scale that up to the millions of images that deep learning would need? So this is kind of the same point Lourdes was making. So we have to go beyond supervised learning if we want to tackle this task. So basically, the situation is we're trying to solve a problem where acquiring annotations or labels is very difficult or impossible or expensive. And another kind of view on this is we're trying to solve an inverse problem that is itself unsolved, or we're trying to learn a fast, train a deep network to solve an inverse problem, and we don't have any existing method that solves it. So it's not like we can just apply some other algorithm. So if we do that, say to get the supervision labels, we just take some classical algorithm and run it on lots of data, then at best, we're just learning to replicate the performance of that algorithm. Another alternative which I haven't really explored at all, but maybe is a good approach, is to use synthetic data. So that has been tried on related tasks, and it can do quite well. The problem, of course, is whether if you train on synthetic data, you can generalize to conditions in the real world. So let me just give like a really quick sketch of what self-supervised learning is, in my opinion, and again, it's similar to Laudez's view. So for my particular task, we have a way of transforming from the kind of scene properties, our model of geometry, reflectance and lighting, to an image. In this case, it's a differentiable renderer, and it's actually something really, really simple. So it's like spherical harmonic lighting, diffuse surface, and diffuse albedo. That's all we're assuming. So like classical computer vision, like the face reconstruction project we heard about in the last talk, would take a real image, compare it to this predicted image from this is our model, and you would use just classical nonlinear optimization, Levenberg-Marquardt, or whatever it is, to optimize these to produce an output that matches the input. The problem is that we know that this task is highly ambiguous, so doing that on its own wouldn't work. It's also prone to getting stuck in local minima and all the problems with sort of classical approaches to this. So self-supervision is that we're going to train a black box CNN to directly regress the solution to this problem, but we're going to train it by using these predictions to recompute the output and then compare that to the input, and that provides a supervisory signal in terms of this reconstruction loss without ever having the ground truth for what this should be. So the sort of general view here is, if you've got a mathematical model that describes the forward process that you want to invert, you can train a CNN to learn the inverse problem without ever having ground truth labels, maybe. Depends on the problem. So this was our approach. This is the setup. So we have a single image, we have some kind of CNN, and it predicts a normal map, an albedo map. Small engineering trick is don't bother predicting the lighting, which is a vector and it's hard to deal with. This is just an image-to-image network. You have enough from the albedo normals and image to solve least squares for the lighting, and you can do differentiable least squares in the network. Okay. Then you have your differentiable renderer, compute your image, measure the difference. But of course this wouldn't work. This is still just doing the same thing as classical vision, and it's completely ambiguous. So the network would probably just immediately converge to a solution where it copies the input image to the albedo map, makes this flat, this is some constant, and it's exactly reconstructing the input. So this is just back to the original kind of problem in shape from shading of the shaded versus painted hypothesis. So are we looking at a violin hanging on the door, or are we looking at a painting of a violin hanging on the door on a flat surface? And of course there's an infinity of solutions in between. So we need some more supervision, or we need some priors. And this is the trick to make it work. There's sort of a few tricks, and you have to have all of them, and if you put them together it works remarkably well, in my opinion. So the first is kind of inspired by psychophysics, that humans seem to have a prior on lighting when they do shape from shading. So this lighting from above assumption has already been mentioned. So the fact that we perceive this as convex is consistent with assuming lighting is coming from above. So we didn't want to enforce something so restrictive as that, but we did think we should have a prior on lighting. So the way we did it was collected a few thousand environment maps, HDR spherical images of like natural scenes, projected them into spherical harmonic space, and then built a statistical model in that space. So this kind of captures in a low frequency sense what natural lighting tends to look like. So like the first main component is this one, which is capturing like side to side rotation of lighting that's generally from above. This component seems to capture like where you've got blue sky, floors tend to be yellow on average in our data set, it looks like, versus a more like, I guess this is direct sun, this is like blue sky, sun not visible or something. So this really helps, this reduces the ambiguity. But the thing that really helps is to take advantage of geometric computer vision. So one of the things that we did do before deep learning, one of the few things that actually worked in computer vision was local features and matching local features, and it works across varying illumination. So pre-deep learning, I used to always tell students in computer vision courses, nothing works except one thing. Look at this, it's really cool. And you can just go on Flickr and type Colosseum in and get 1,000 images of the Colosseum, detect SIF features, match them, do some clever geometric computer vision and get really good estimates of the scene geometry and the camera positions. This is really useful for us because the illumination in these images can vary dramatically, and then using the model and the camera poses, we have correspondence. So effectively, it gives us images with changing illumination. We can cross-project to get this sort of thing. Right. If this diagram confuses you, don't worry. It confused the reviewers as well. They didn't know what the hell was going on in this. So let me just try and give you the gist. Offline, we collect images of scenes, like monuments and that kind of thing, and we apply multi-view stereo, structure from motion and multi-view stereo. So we have a good 3D model and accurate camera poses. That gives us two things. It gives us depth maps from which we can compute rough normals, which we can use to directly supervise the estimated normal map. That's quite helpful. But the other thing it lets us do is cross-project between views. So if we have a pair of images that are looking at the same part of the scene, and we have a depth map and the relative pose, you can cross-project between them. And that means if you have something that is a photometric constant, like albedo, you can estimate albedo, cross-project, and then measure the error between the two conditions. So it's effectively saying, it's like giving you two views of the same scene under different lighting and saying that some things should remain the same. So that's it. And then so at training time, you do Siamese training with pairs of images. You do this cross-projection, and one of your losses says the albedo should be constant. So if you put that together, it really works. So you can take a single image, nothing known about it, nothing known about the camera, and you predict an albedo map, illumination, and this is our normal map. For comparison, this is the normal map from the multi-view stereo supervision. So it has lots of holes. It doesn't pick up the detail in this part of the image. Also, this was from 500 images. This is from 1. So to me, this is like a miracle. It's a miracle because I spent 10 years doing shape from shading and getting just garbage out, like I'll show you in a minute. This is just a rendering of our normal map with uniform albedo and frontal lighting. So this is maybe the image to look at if you want to get a view of what the estimated geometry looks like. We compared to some other stuff. Of course, it's better. That's how we got the paper published. This is like a classical, this is SURFs. So this is classical, model everything, stick it in a nonlinear optimizer, get garbage out. Again, garbage, we get this nice, highly detailed normal map. If you're still a bit skeptical and think, yeah, but he's handpicked the 5 examples where it worked, really it works. This is a video off YouTube in front of York Minster. And we're just applying the network per frame, no temporal smoothness. And if you look at the normal map or the re-rendering of the geometry, we're really getting a lot of the detail, and it's reasonably temporally consistent. Same for the lighting as well. The albedo image is also kind of interesting, with shading factored out. Right, I've got a few minutes left. So in the talks this morning, people kept mentioning interesting things, and I would email my student and say, oh, run this image, it would be cool to see what it does. So this is now the results of that. Okay, so to set this up, what is this network actually doing? Is it learning shape from shading? I'm not sure really. It might be. It's actually, I think it's learning shape from everything. It might mainly, and this would be a little bit disappointing, be learning shape from kind of semantics or shape from recognition. So it just, it doesn't explicitly know that something is a window, but it's seen so many examples of windows. It just, a neuron fires that says this is like all those other windows you saw, and a few parameters to describe its pose and stuff, and it just pastes it in and blends it. Something like that. But we can kind of test this. Does it learn any general principles of shape from shading, say? So it's trained on outdoor scenes of mainly buildings and monuments, like tourist images. So what if I give it this, which people were, this was a nice illusion in the last few months. Have people seen this image before? So it's interesting because it's side lit. So in this case, the convex concave interpretation is quite variable, and for a lot of people, you have one interpretation of all of it, and then when you look at one of them, it changes your interpretation of all of it. Anyway, what does the network do? So it does give you I think like this shows it is learning something about shape from shading, because there's no semantics here really that it's seen before. It's not consistently resolving convex concave, which is kind of interesting. This one's convex, this bit's concave. And I think this might be because it's side lighting, which it doesn't usually see. Now I've just rotated the image so it's lit from the other side, and again you get a mix. If you show it these two, which is like top and bottom lighting, it is kind of interesting because it resolves them both with top lighting. You'll have to sort of believe me, it's a bit hard to see from the normal map, but if you integrate the normal map into a height map, you can see. So for example, so this one, the top is the normal is pointing up, it's resolving it as convex, which is a top lighting interpretation, and here this part, for example, is concave, which is a top lighting interpretation. Volcano crater, it does the same, it does what a human would do. So when I integrated these in MATLAB, I should have put it in, but this is a volcano, this is a crater. Right, a talk this morning had mirrors in. I wanted to see what it would do with mirrors. It does what it should do. It has nothing in its losses that would allow it to understand that that's a planar surface. So it just reconstructs like the reflection in the mirror, not surprising. What does it do with a trompe l'oeil? Again, it behaves kind of sensibly. These results are not cherry-picked at all, so they're quite ugly. This green is like a ground plane pointing up, so it's basically estimating a ground plane for that water, which kind of makes sense. Then this one was weird, trompe l'oeil of the Louvre. It seems to not so much fall for this, and I think it's because in the training data, the ground plane is a really, really strong supervision signal. We actually dealt with that explicitly, so I think it's kind of learned to segment the ground plane and just give it a constant normal. So, the summary is, I think the main takeaway is that, well, you're used to hearing this now. A CNN can solve a really hard problem, okay? But in this case, it's a little bit more interesting because getting the supervision right is quite hard. And also, it satisfies me a bit that it's had to learn from a physics-based model. So the gradient it's getting back from that self-supervised loss is coming from Lambert. Isn't that great? So the criticism of this would be that all models are wrong. Like, Lambert's law doesn't describe surfaces you see in the real world. That's, clearly a really limiting assumption. So a reasonable question is, shouldn't you make that part of the model partly learnable or fully learnable? And then there's a broader question that, like, some people believe that any attempt to impose human understanding or domain knowledge on deep learning is just always eventually going to be beaten by learning everything, and maybe they're right. I think I've got 31 seconds left, so can I just put one picture up? Just to show you where we're going with this. So if you take the reconstructed models and try to re-render them, they look a bit naff, okay? Yeah, it looks like the lighting's changed, lit from a different direction, but you're not going to believe that's a photo. So the thing we've been doing since is combining this with neural rendering, where you basically try to learn, you train another network to transform that into a photorealistic image with a GAN, and it works. So these are now relit. The cool thing is it learns to hallucinate skies that are plausible given the lighting in the image. Right, I will stop there.